Okay, welcome to the start of 11.2, page 172 onwards. This is question 1. I'll do all of it probably in one video and then take some individual questions and do some other shorter videos, probably. That's the plan anyway. Now, we're playing with tangents and chords. Just to remind you, here's a diameter, for example. This is part of question 1. Passing through the centre O, that's a diameter. A chord is any old line cutting through the circle, touching the circumference in just two places, but it's not, the longest length through the centre. That's called a chord. And any straight line touching the circumference in just one place is called a tangent. So that's another tangent touching the circle. That's another tangent touching the circle. Alright, so here we go. Let's work out some angles now. Now here's a rule. We've got two tangents meeting outside of the circle, coming to a common point and forming an angle. Well, if they do that, then we have formed an isosceles triangle. So if that is 66 degrees, A is going to be 180. Take away the 66 and then divide by 2. So let's just do that quickly. That's going to be 180 degrees. Take away the 66 and then divide it by 2, because I've actually got two A's there, haven't I? So let's just give you a quick answer there. 180 take away 66 equals, now divide by 2, so angle A is 57 degrees. That's that one done. After A comes B. Very, very easy. We have a tangent touching the circle in one place. Now here we have a radius, because this little line goes up to the O, which is the centre, and you will recall that this is 90 degrees. The tangent to the radius forms an angle of 90 degrees. And I've got a very simple triangle there with a 40 and a 90 and a B. So B is going to be 180, take away the 90, take away the 40, so B is going to be 50 degrees. Alright, lovely. Same again with C, same sort of thing. I've got two radii touching two tangents. I don't need to know all of that information, because I'm going to work with this triangle right here, because that's where the 40 is. So that's 90 degrees, and C is going to be 180, it's a triangle, take away 90 due to the tangent to the radius, take away the 40, and so C is going to be 50 degrees. Is that alright? Just like the other one. I think that's correct. Yeah, that's that one. Now coming up here, yes, I know that's a tangent, and I know this is 90 degrees, not because the tangent is touching the radius, but because I have a diameter there, and the angle at the circumference that's been drawn from the diameter is 90 degrees with the circumference. That's not going to help me in this case whatsoever. What it will help me with is as follows. The alternate segment theorem, and I'll read it out to you, states this. Once you've seen it, it's really easy. So let me state it. It says the alternate segment theorem says that the angle between the tangent, that one, and the chord, that one, is the same as the angle in the alternate segment. So if you can imagine this little piece here being a segment, the rest of this circle here is the other segment, the alternate segment. Essentially, the 35 degree angle made there with the tangent and that chord is exactly the same as the angle inside the triangle in the other section of the circle, the alternate segment of the circle. Therefore D is 35 degrees straight away. There's no further calculation. It's a question of spotting this grade A rule, and it is grade A. Alright, that's that one done. Here, what have I got? A complicated arrangement. I reckon I'm supposed to use this, but I can work E out in two ways. I'll come back to that. Let's just do F, because it looks quite easy. A tangent of 91 degrees touching that, I don't accept that. How can that be 91 degrees? It's a tangent touching a radius forming an angle of 91 degrees. That's ridiculous. Doesn't make sense. It's got to be 90 degrees mathematically. I'm going to pause that and see what the answer book says, because I'm not accepting that. Really not happy. There's two ways you can work this out. You can go with the mistake that's in the book. It is impossible for a genuine tangent to touch a genuine radius and to be 91 degrees. It does not work. Here's another way of doing it. This is supposed to be a diameter because it passes through the center 0. If that is a diameter, then you know that the angle of the circumference will be 90 degrees. I told you this a couple of times. Look, there it is again. Diameter 90, radius, tangent 90. It all fits. If that's 90, then I've got an isosceles triangle because I'm told it's isosceles because it doesn't have to be, but I'm told that it is. Therefore, the angle F there will be the same as the angle F over here, and that's going to be 180 degrees. Take away the 90, and then you divide by 2. And of course, that's 45 degrees. That's one way of doing it. Now, if I deliberately allow this mistake of 91 degrees, I've got a different answer. I'm going to do it in a different colour. Sorry to confuse you, but if that's 91 degrees, then according to the alternate segment theorem, this angle should also be 91 degrees. Okay, that's in this segment of the circle, and that's the alternate segment of the circle. And if that's to be believed as 91, then that's also 91. So my calculation is going to be 180 take away 91 divide by 2, because it's still an isosceles triangle. I'm going to get 44.5 degrees. Well, that's very silly. Take your pick. The question's one big mistake. Let's go off to G anyway. Just go with the red one. Red is correct, so you have to believe it, and that is just a nonsense. Put a couple of crosses down there for you. G. Right, this ain't too bad, is it? 120 degrees. That is a tangent. That is a radius. That is the centre. That is 90 degrees. 120, and that's a straight line. This is therefore going to be 60 degrees. There it goes. I've got a 60, a 90, and the leftovers. So G is going to be 180 degrees. Take off the 90, the tangent, with the radius. Take off the 60 on the straight line, and that will give me, let's just take a look at that, 90 take away 60 is going to be 30 degrees. That's nice and comfortable. Now back to this one here. Two ways of doing it. I can see both ways. Let's just do the easy way. This is 160 degrees. This is touching the centre of the circle, which means, friends, that is an isosceles triangle. If that's isosceles, then this part of the angle is going to be 180 degrees. Take away the 106 degrees, the large obtuse angle, divided by 2. And that's going to give me something quite nice. Take away 106, now divide that by 2. Therefore, this part of the angle within this small triangle there is going to be 37 degrees. Now look, here I have a radius, here I have a tangent. Therefore, this part here, all of it, is 90 degrees. So angle E is going to be 90 degrees. Take away this small red part here I worked out a minute ago, which is 37 degrees, and that will therefore give me 52 degrees. I've made E 52 degrees, alright, by calculation. But look here, the angle at the centre is 106, and the angle at circumference, I've made a mistake here, just check my calculations here. E is going to be, just check here, press the wrong button, 180, take off 106 equals, divide that by 2, 37 degrees. And 90 take away 37. Oh, 53 degrees. Oh, that's my mistake. Okay, the moral of the story is don't use your head, use your calculator. So 53 degrees, very silly. Yeah, look at that. 106 degrees. As you know, angle at the centre is twice as big as the angle at the circumference. Therefore, that is also 53 degrees. It didn't ask me for it. They could have called this angle F or G or anything. But incidentally, it's just wonderful, isn't it? Now, 53 degrees is there. 53 degrees is outside there, which is angle E. But look very, very carefully. Can you see that angle E, according to the theory of the alternate segment, that angle E will be whatever this angle is right here. And I've proved that this angle is 53, and I've also calculated that angle E is also 53 degrees, not using the alternate segment theory. So there I go. I've done it the old grade B way. The old grade A way would be to say 106, halve it, 53, and look, E is an alternate segment, is an alternate angle, to 53, angles in the alternate segments are equal, therefore E is also 53. So there's two ways of calculating that. I am very sorry about this one down here. I apologise for the mistake there. I've worked it out both ways. The answer book says 44.5 if you obey the 91. If you obey the mathematics of what the diagram shows, that has to be 90 degrees both there and inside there, for two reasons. If that was 90 degrees, then the alternate segment theorem says that also has to be 90 degrees. If that being the case, it also holds really well, because if I have a diameter, then the angle of the circumference coming from a diameter as a chord is also 90 degrees. And so there you go. Big mistake there. I'm going to pause there and cry because you've had to suffer with me with this one.